Welcome, everybody. Welcome to a new semester, and welcome in particular to Physics 321, Classical Mechanics. So my name is Morten Hjorth-Jensen, and I'm going to be your main teacher. Julie Butler is our teaching assistant. And then in addition to the two of us, there is George McClure, who's one of the undergraduate learning assistants, and Abby Fallon, who's also another undergraduate learning assistants. We have planned these classes as a flipped classroom. So we're going to dedicate Mondays to regular lecture days. Wednesdays may be a mixture of lectures and problem solving. I mean, the first 2 weeks, we will mainly do lectures. And then Fridays are planned fully as flipped classes with problem solving, a summary of the week, and discussions of exercises and projects, and so on. So what we would like to do now, before we dive into our first topics, which is essentially a repetition of what many of you have seen before, is to give you a background and an information where you find the basic course material, where to download exercises, where to find lecture notes, and so forth. So the lectures will be in a hybrid mode. We are going to attempt to have in-person classes, but we know that many of you may not be able to be there physically. So the lectures will also be broadcasted via Zoom. The lectures will be recorded and they will be uploaded after the classes, and they will be put under the weekly schedule, which you can see in the file here, just a little bit down here. So if you go scroll down a little bit, you will find the weekly schedule. So after every lecture, we'll actually upload the video of the lecture under the specific day. We are also going to upload the lecture notes, or the specific notes which we wrote down on the whiteboard. So the whiteboard will function as a classical blackboard, and they will also be uploaded here. But you will also find them under the doc folder. So if you go up again and you look at the doc folder here, so in here, you will find the handwritten notes for the given year and the given semester. You will find the textbooks which we're going to use. So on the literature here, you will find a selection of textbooks. We are coming back to those a little bit later. The main textbook is a textbook by Taylor, and there is a PDF version here of that specific textbook. So you will find a lot of information here. For those of you who are familiar with Git as a version control software and GitHub as a provider where you can store your files, you can easily navigate along these different folders and download everything to your own laptop or PC and use that material as your own material. This is actually one of the things we would like to happen, that you can take over this material and then just tailor it to your own needs and your own interests. Now, we are going to give you a brief overview of where you can find the different lecture notes, slides, exercise sets, and so forth. So there's a link in the upper right corner here. If you click on this link here, you will get straight into the weekly lecture material. So if we take a look at that, you will get into this overview of course material. So if you look at the specific week which we are in now, you can either look at the standard PDF format for the lecture notes, or you can just look at one of these HTML files. And like the plain HTML is nice for searching after specific things. And then there's also Jupyter Notebook if you wish to use that as a starting point for making your own notebooks. And if you scroll down here, you will find the exercises, the weekly assignments and exercises. And the first homework set, which is set for January 21st, comes both with a PDF file of the exercise. There's a LaTeX file if you would like to typeset things, typeset mathematical equations using LaTeX as a typesetting program. there is just an HTML format. And then there's also a Jupyter notebook, which you can use as a starting point for solving the exercises. Now, when it comes to the exercises and the midterm projects and the final exam project, you can hand in the paper and pencil exercises as a scan of your handwritten notes. Alternatively, if you're familiar with the typesetting mathematical formula, you can use a Jupyter notebook, or you can attach a PDF file with your answers to the exercises. For the numerical exercises, and we are going to have numerical exercises every week in order to deepen the type of problems, to deepen your insights about the physics and the type of problems which we're going to deal with, you should always hand in a Jupyter notebook. The schedule for the semester, if we go back to the main website for the course, where you find most of the basic informations and the different links, you will find a given schedule, and so the lectures are given by me and Julie when we have flipped classrooms. The lectures are from 3 to 3:50, Monday, Wednesdays, and Fridays. We are planning to have office hours immediately after the classes, so we can hang around here till roughly 5 o'clock. If you cannot, you're always invited to just send us an email or use Slack, and we can make an appointment. You can meet one of us. In my case, you can always send me a text. You have my cell phone number here, or just shoot me an email. We can set up a Zoom session, or we can just meet in person. So this is very much up to you, what kind of format you would like to. We invite, you should feel free to just set up an appointment whenever you want. But as a kind of default, we are going to have office hours from 4 to 5 o'clock, right after the lectures here. Now, Julie has also her own office hours, and there's one session in BPS, and then there's another virtual session. And similarly, Abby and George, they also have office hours here. If there is an interest in having additional classes, we can always set up that in case there are things you would like us to deepen, something has been unclear, or just something extra you would like to know something about. There's also the possibility of doing an honors project. If you go back to the top of this website and you click on the doc folder here, you will find a list of honors projects which we have been developing over the years. So there are PDF files and also LaTeX files of the projects. We invite you to take a look at them and see if this is something which could interest you. So if we go back, let's take a look at both the grading and the plans for the semester. So you will find the grading and the percentage of the total score listed here. We are planning to have 2 midterm projects. So we won't have a regular midterm exam of 50 minutes where you're just sitting there and sweating and trying to find the answers to the different problems. We will roughly have a week at our disposal to solve the project. The projects will be a mix of paper and pencil exercises and numerical exercises. So as we said, every week there will be a numerical exercise. And many of the programs you're going to develop, they're going to be lookalikes. And it means that when you come to the midterm project, you will often find that you only need some small perturbations of the different programs you have developed in order to solve the midterms. So the 2 midterms have a deadline. So we put one deadline to March the 4th, and another one to April the 8th. These deadlines are for your planning of the semester. It means that in case something goes wrong or we need a little bit more time, we can always change the deadlines. But as they stand now, these are just a suggestion from our side in order so that you can plan the semester properly. The final exam instead of having a typical classroom exam of 2 to 3 hours, we're also going to replace that one by a 1-week project. That's going to be available the Friday before the deadline. So the grading scale, you can find that one here. The 2 main textbooks are given by Taylor's book. That's going to be our main text. But since we will also have many computational exercises, there is an additional textbook which many of you will find pretty useful. It contains many Python examples on how you can solve the problems which you're going to face every week. That textbook is a textbook which you can download for free if you are at the university and use an IP number of the university. So that if you go to the MSU library, you can actually download this textbook for free. We provide you with a PDF copy of Taylor's textbook in case you have not been able to buy the textbook. Then our weekly lectures, they are collected as a Jupyter book. And the Jupyter book, if you click on this link here, you will be directed to the Jupyter book here. And that contains essentially an extension of the weekly teaching material as a book. And you can search all the different chapters. It's containing the teaching schedule and the various chapters and topics which we will cover during the semester. So it means that the weekly material, which you find in the link here at this specific place, all this material has been collected and extended upon with a little bit more text as a Jupyter book here. Now, the disadvantage of a Jupyter book is that you cannot run it as a Jupyter notebook as you're used to. But if you click on the icon up here, you can save it as a Jupyter notebook, and then you can run the different examples which are in there, or you can just save it as a PDF file if you prefer that, and print it whenever you find it convenient. So going back to the main website here, if you scroll down here, you will find the teaching schedule. This is just a suggestion from our side. And there will also be weekly reading suggestions. As you can see here, we have a reading suggestions of different chapters from the textbook of Taylor. And we will try to cover these topics every week. So this contains roughly the weekly schedule here. Now, you should feel free to ask questions if things are unclear. If you're not finding the right material, never hesitate to ask questions. So the basic information is contained at this site here. And if we now move on to the topic for this specific week, what we can do then is simply to dive into one of these files here. And this week starts, as we've done, with a presentation of where you find the material, useful tools, and we're also going to remind ourselves of many of the topics which you've seen before. So I hope you don't get offended if we spend some time on repeating things which many of you may find obvious and which you have seen in previous courses, but it's very easy to forget things. And so these slides are meant as a kind of reminder and also to get us started with the basic topics which we want to cover. The exercises for this week with a deadline not this Friday, but Friday, January the 21st. These exercises contain essentially a kind of review of material which you may have seen before. And these are things which we will need when we move on. But let's take a look at some of the basic topics which we need to remind ourselves about. So classical mechanics is a topic which has been taught intensively over several centuries. It is, with its many variants and ways of presenting the educational material, normally the first real physics course which we encounter. And many of the equations and the ways of reasoning about the underlying laws of motion and pertinent forces, they do actually shape our approaches and understanding of the scientific method. as well as the way we develop our insights and deeper understanding about physical problems and systems. So if we look at the classical mechanics, one of the things we often start with is, when we are going to solve a problem, is to define the choice of origin. We would typically have the most common choice is to start with a Cartesian coordinate system in either 2 or 3 dimensions. We are going to choose the direction of the axis. We may choose the positive direction, whether this is a left-handed or right-handed system of reference. We may choose units and dimensions. We are coming back to these quantities. These are important topics when we are setting up a physics problem. So one small aside before we look at the next set of questions. So one of the things we are hoping here with this specific course is actually to make you actually fall in love with the scientific method and doing science at perhaps a different way, in a different way as you've done before. And the mix of numerical exercises, computational problems, and paper and pencil exercises, our hope with that is that doing science with all possible tools will allow you to deepen your insight about, in our case, physics and classical mechanics. But the other hope is that this will allow you to see how we actually do science using all possible tools to solve scientific problems. So we do really hope that you will enjoy this specific way of doing physics in particular, but also doing science in more general terms. Now, if we now go back to physics here, one of the things which is important when we do classical mechanics, which is normally also called Newtonian mechanics, which means that we freeze out quantum mechanical degrees of freedom, or relativistic degrees of freedom even. The system is normally independent of the origin of axis. So whether we have defined the origin in one specific point or the other point, that shouldn't affect, let's say, the final energy of the system. So we normally call that kind of independence or invariance of as translational invariance. So if I were to translate my system from one point to the other one, the basic physical laws should not change. And that means that the observables which we get should not depend on our choice, on our specific choice of axis and origin. Similarly, if we look at the directions of these axes, if there are some specific privileged axes, some orientation of the systems, the physics and the physical laws should be independent of that. That leads to what we normally call a rotational invariance. So you could think of having a three-dimensional Cartesian system which you are rotating by a specific angle. Now, your physics, the output of you doing physics, the energy of the system, or other types of observables should not depend on a specific privileged axis which you have chosen. So often you would choose that because perhaps your calculation is easier if you choose one specific set of coordinates compared to another set of coordinates. So one thing you will encounter in many physics cases is that if you make a transformation from Cartesian coordinates to a system with spherical coordinates, sometimes you can even find an analytical solution to the problem. Now, another thing, if you think of the orientation of the system, whether you've chosen a left-handed or right-handed system of reference, the physical laws should not depend on that. This is a statement which needs some modification, because if you look at quantum mechanical systems, and if you're looking at the process like a beta decay, that can depend on whether you're looking at a left-handed or right-handed system of reference. Now, the final question is whether the physics is independent of the scale of the length. So if I were to multiply, let's say, my length with some constant, I mean, the only thing which would happen then is that my results would scale with this constant which I've been using. It's pretty obvious if we use our intuition. However, we have to be a little bit careful with that statement because physics, and this is a very important point of view, when we are doing physics or science in general, we are always looking after effective degrees of freedom. Which are the degrees of freedom which pertain to a specific system at a given length and energy scale? So Newtonian mechanics, as you will encounter it in classical mechanics, is not the best possible theory when you want to describe the micro world. So if you want to perform studies of quantum mechanical systems, Newtonian mechanics will not be able to describe the physics of the systems properly. And that's where you need quantum mechanics. What it means is that if you stay with Newton's law as your equation of motion, if you wish to describe quantum mechanical systems, you would have to replace Newton's equation with Schrödinger's equation in order to describe the system. So that would be in case relativistic effects are not very important. If you're dealing with relativistic effects, you may have to switch to something which is called the Dirac equation. If you're dealing with spin half particles, or if you have particles with integer spin numbers, you would have to deal with something which is called the Klein-Gordon equations, and many, many more complications. So if you look at that last statement, within Newtonian mechanics, the validity of Newtonian mechanics, the physics would be independent of the scale or the length of the system. However, if you're looking at very small length scales, it may happen that Newtonian mechanics is not what you should use. Now, if we move on a little bit now, one of the things we would like you to remind you about is actually dimension units and some labeling here. So we are going to deal with several quantities. So if you see a bold-faced quantities like this one, this is going to indicate the position vector r. In one dimension, we will normally just use x. We will reserve the letter n for mass, t for time. So these are the basic quantities. And then we can always put together these quantities here into velocity, which is the same as in terms of the position and time. It's the same, it's given by position divided by time. So the dimension of velocity is position divided by time, or position over time. Acceleration, a. If we're just in one dimension, there will not be a bold-faced symbol. Sometimes we will write this with a with a subscript x to indicate that this is the acceleration in the x direction. And similarly, we would have an a y with a subscript y in case this is the acceleration in the y direction. Similar for the velocity, the momentum p. We will use the letter k for kinetic energy. And for potential energy, we will use the letter v. And for frequency, we will use the Greek letter omega. And you can define many more variables as we will need them, as we may need them. But these are some of the central variables which we are going to use in this course here. And position, mass, and time are some of the fundamental variables in classical mechanics. If we then look at the dimensions of these quantities, there is a kind of sloppy physicist notation where we are going to replace, not replace, but indicate the dimension of a given variable by using these brackets. So R has dimension length, N has dimension mass, K, which is the kinetic energy, has obviously dimension energy. And time, obviously, given by T here, time is the dimension of T. The velocity is length over time. Acceleration is length over time squared. And the momentum is mass times length over time. and the frequency is inverse time. Now, this plays, this kind of dimensions and units, they play an important role when we are setting up equations and when we want to solve these equations. Because often when we solve physics equations, one of the things we want to do is to simplify the equations. That means often that we want to get rid of some constants. And we end up very often in equations which have no dimension. That means that there will be some constants which we then would have to multiply with our solutions to the equations in order to get the right dimensionalities. So typical units which we end up using for length are meters, for mass are kilograms, and for time, seconds. So these are the typical units. So keep in mind the distinction between dimensions and units. So dimension is a much more fundamental quantity. Units are more the kind of entities which are adequate for a specific type of problem. So sometimes we may use kilometer instead of meters, and so on. Now, if we go back to some of these definitions here, there is actually a reason for why we would like you to remind yourself a little bit about these quantities and their meaning. So let's take a look at the famous equation here. And now we're going to switch to the whiteboard. So let's do that. So when you're solving physics problems, whether you do that by paper and pencil or you do it numerically, a very common thing which you end up doing in order to prepare the equations for either an analytical solution or a numerical solution is to render the equations dimensionless or to get rid of some of the physical constants so that you can really simplify the equations. That means that when you solve the problem, you would have to bring these constants back again. But let's now remind ourselves of Newton's equation. So Newton's law, if we now write it down here, so we have the force, and we are going to look at the system in one dimension now. So that means that this F could be the force in the x direction, but we are simply going to use the letter F here. And this is given by the mass of the specific object, and then the acceleration here. So the acceleration is now a scalar, it's not a vector, and we're simply looking at it in one dimension here. So we should actually emphasize that this is Newton's law in one dimension, and then we don't need to bring in the vectors here. What we also know is that the acceleration, the instantaneous acceleration, is given by the derivative of the velocity with respect to time. So we would have a dv dt. And you see now that that brings in the right dimensionality. So velocity is mass, length divided by time. And we have another time here. So we get length divided by time squared, which is the dimension of the acceleration. Now, this again is actually the derivative of second derivative of the position. So we would have a d dt, and now I'm going to use the letter r for position, even though since this is a one-dimensional problem, I could equally well have written x here. So this would be dt. And this is written in a more compact form in terms of the second derivative with respect to the position r. Now this is Newton's, when we now plug it back again, what we would have is F is equal to mass times the second derivative of the position. Now what is common now is to try to make these equations dimensionless or get rid of some of the quantities and make these quantities dimensionless. So a pretty common procedure is to introduce a dimensionless time. So we would now define a dimless time. And we are going to call this variable for tau. And that's given by a constant. As we said before, we are scaling the equations with a constant multiplied with t. Now, t has dimension time. So that means that this alpha here, if we're now using this kind of odd notation, which is going to mean the dimension of a specific quantity, this has to be 1 divided by time. So this is inverse time. And then tau becomes a dimensionless quantity. So when we plug it back into the equations again, what we end up with then is an equation here with f, which is now given by m times this quantity alpha squared. And we are now assuming that alpha is a constant which we have defined. As you will see later, when we are looking at specific physics cases, this alpha may introduce a natural timescale for that specific system. If we are setting up a dimensional position or length, it's going to reflect a natural length scale for the system, which is dictated by the physical constants, which are specific for that system which we're looking at. So what we would end up with then is an equation now where we would have the second derivative of the position r with respect to this dimensionless time. Now, what's normally done is also that we would try to get rid of these constants by dividing them both sides. And then we have a right-hand side, which now contains this dimensionless time. And what you see now is that the dimensionality of the left-hand side and the right-hand side is now simply just length. In our previous case, the dimensionality was given by mass times length divided by time squared. Now we have actually simplified the problem, and we have only one quantity which has a specific dimension. The other quantity tau is dimensionless. So this quantity here, if we look at this one, the whole quantity here, this has now dimension length. Now, one of the many reasons why we do this is not only because we want to simplify the equation, but it means that when we are solving the equations numerically or analytically, particularly when we're doing it numerically, is that the equations can then be programmed in a much simpler way. So we can actually develop a very generic problem or program which solves our problem. And then when we are looking at the specific problem, the only thing we need to do is actually to multiply the solution with the physical constants which are specific to that problem we are looking at. You're going to see this again and again and again in this course. Since we are going to solve many problems numerically, what you will see is that you can write a pretty simple and general program and solve a great variety of physics problems. And the only thing you need to do at the end is to multiply your solution with the appropriate physical constants. So if you look at the right-hand side here, this is a right-hand side which we could have simplified further by making length dimensionless as well. That would give us another constant. And then we could solve an equation for the second derivative, which only depends on dimensionless quantities. This is also very convenient because some of the quantities which we have, some of the physical constants, may vary a lot in values and range, which again means that having to plug in these constants can lead, one, to errors because we punch in the wrong constants, or it can eventually lead to some numerical problems like loss of numerical precision because some of the constants can be way too large or they can be way too small. So doing this is something which you will see is a pretty common practice in numerical solutions of physics problems, but also in the analytical solutions. So just to give you an example, if you think of the gravitational force, and if we are looking at the gravitational force between two objects, object 1 and object 2, this is going to be a force which is a function, and now we're putting a vector sign here. So this is a function of R1, the positions of object 1 and the position of object 2. This is given by the gravitational constant. It's multiplied with the mass of one of the particles multiplied with the other one, or the two objects. And then it's given by the relative distance between the two objects squared. And then there's a vectorial dependence. So let's take away the vector sign here and just think of this in terms of the absolute value of the magnitude of the force. Now, in this specific case, what you see now, when you want to do a dimensional analysis, you will then find that this parameter G, when we look at its dimensionality, that is going to be given by length squared, length cubed actually, divided by mass times time squared. And actually the value is given by a number times 10 to the minus 11th. So it's a constant which is very small. And if we just deal with a constant, we plug that one in directly in the equations, it's very easy for us to write in the wrong value, but it can also lead to, as we said, to loss of, say, numerical precision. So this was a kind of small digression because we wanted to anticipate some of the topics which are coming pretty soon. And thinking of the dimensions and making a dimensional analysis of the equations is a very important, how to say, process, and where we prepare the equation for either an analytical solution or a numerical solution. So let's go back to the slides in the meantime. So one of the other things which we are going to deal with are obviously quantities like scalars, vectors. We are not going to emphasize matrices. So matrices, since many of you have not taken a course in linear algebra, this is something which you will not see in this course. Some of you may have taken a course in linear algebra, but we are not going to use matrices in this specific course, but we are going to encounter vectors and we're going to encounter scalars. So when we set up a vector, so a typical vector will be a boldface quantity. On my whiteboard notes, since making a boldface symbol is a little bit more tricky, you will see the vectors as a letter with an arrow on top of it. So when we define a vector here, this would be an AX, have a component AX, AY, and AZ, if we are dealing with a system in 3 dimensions. And it's pretty common to write this out when we're looking at the vector in terms of unit vectors. And the textbook of Taylor sometimes mixes different definitions. So it's pretty common to write the unit vector, let's say in the X direction as an E1, the one in the Y direction as an E2, and the one in the Z direction as an E3. These are unit vectors, which means that they are absolute values, so their magnitude is equal to 1. So I equal to 1 is also a common notation, so that means that you could see this E1 being replaced by the letter I, a boldface letter, E2 being replaced by J, and E3 being replaced by K here. So a notation which you will also encounter in several textbooks, instead of E1, E2, E3, is I, J, and K. So we may mix a little bit unintentionally between these different notations. The textbook is actually doing that, and many other textbooks, sometimes they're not fully consistent. So when you look at another type of notation which you can encounter is something like this, which could be more generic. It doesn't need to refer to a Cartesian system. So this could be an A1, which could be if you're making a transformation to spherical coordinates, so E1 could be the unit vector for one of the angles, and E2 for the other one. So if you make a transformation from a Cartesian system to a spherical system, to spherical coordinates, you may have different so-called unit vectors. So some people, when they write the notation for the vector as we have it here, it may not refer explicitly to, let's say, a Cartesian system. So it's a little bit more general. If we are dealing with polar coordinates, we would have typically position R given by X and Y, as you can see here. And then we would have the unit vector in the X direction and the unit vector in the Y direction. And we can make a transformation here to polar coordinates where rho is defined from 0 to infinity, and it's actually given by x squared plus y squared. And then there is an angle phi, which takes values from 0 to 2 pi. And the transformation which you would deal with then are given by rho times cosine phi and y given by rho times sine phi. And then you can define phi in terms of the inverse tan of the ratio between y and x. And then you can rewrite A in terms of the new coordinates. So sometimes it's more convenient to run calculations in one specific coordinate system. And polar coordinates is one of the systems which is often used in solving physics problems, in case these degrees of freedom are more handy when it comes to find, let's say, an analytical or a numerical solution. So sometimes you can reduce, let's say, a two-dimensional problem to a one-dimensional problem by a smart transformation. Similarly, you can reduce a three-dimensional problem to a two-dimensional problem. Or what happens then is that one of the dimensions has a trivial solution and the other two dimensions or the other one dimension may have to be solved numerically, or you could find an analytical solution. So these are all types of transformations which many of you have seen. We have collected many of these equations here. So for you to look them up again. There are many other definitions. We have definitions of dot products between two vectors. So that means that we have the magnitude of A and B multiplied with the angles of cosine of the angles between A and B. So these are equations which many of you have probably seen before. And in some textbooks, they would also define the unit vectors in terms of a hatted symbol. So we are going to stop here. And on Wednesday, we are going to look at how we can actually solve some simple physics problems. And we are going to look at a falling object. And we're going to set up how we can solve this analytically and how we can solve it numerically. And that's going to interface with one of the first numerical exercises, which we have in the first set of exercises. So this ends today's lecture. And hopefully you have gotten an overview of where you can find the material. Remember never hesitate to ask us questions if something is unclear, if something is missing, if you cannot find the exercise set for that specific week, and so on and so on. We invite you also to take a look at the material which you see here. Feel free to skip what we write about matrices, because that's something which we will not cover, and we will not use matrices in this specific course. But there are other quantities here, like the dot product of two vectors, the norm of a vector, and the kind of notation which you may have seen in mathematics courses. Also, for those of you who are a little bit more familiar with linear algebra, you may have seen the dot product of two vectors in terms of the transpose vector times the vector. So we have a transpose of the vector A multiplied with a vector B. And that reads as the sum of the multiplication of the different components. So if I could be the X and the Y and the Z degrees of freedom, so this will be the X components plus the Y components plus the Z components. So take a look at many of these equations here and remind yourself a little bit about some vector algebra and some of the equations which you will find throughout here are things like the cross product of two vectors. You will also find derivatives of a vector with respect to a scalar, like the equations which you see here. So the derivative of the acceleration is given by the change in velocity per unit time, and it would have components like this. There are examples of other quantities like the gradient operator, the secondary, the curl, and also the Laplacian. So the Laplacian is a scalar. And these are quantities which you are going to encounter again and again in this course here. So take a look and remind yourself of some of these quantities. And then in the exercises, you're going to actually use some of these equations here. You will need them in order to prove some of the relations. And when we're done with that, so as I said, matrices are things which we will not cover, and that deals also with rotations and transformations of basis sets. This is more stuff which is more important, I would say relevant if you've, or useful if you've taken a course in linear algebra. But where we are going to start on Wednesday is to look at a first physics case, which in a way sounds a little bit boring. It's that of a falling object. And we're going to see how we can solve that numerically as well. So this concludes our first lecture. Try to look at the exercises for the first problem set, because that is meant as a kind of reminder of some of the vector notations and vector properties which we will need when we are going to solve different exercises. So this concludes our first session, and we look forward to see you again on Wednesday. Best wishes to you all.